All right, guys, welcome back to another lecture video here. Today we're going to kind of change gears a little bit. We've been talking an awful lot in these last two, specifically about this H, right? This idea of enthalpy or delta H, even more specifically, right? Change in enthalpy or change in heat energy. Now, thermodynamics is not necessarily only about delta H or this change in enthalpy, right? And table I stuff, right? That's all well and good, but there are other ways that we can go about measuring different things in thermodynamics. Now, the next one we're going to kind of learn about very briefly here is known as entropy. Right, so it's a little bit different. Kind of sounds like enthalpy a little bit, but it's entropy, and it's actually measured with this variable of capital S here. Right, it's the measure of disorder or randomness. Now, you might be wondering, well, how the heck do we go about measuring disorder or measuring randomness? Right, it's just a general process, more wider lensed here. Right, so is that wondering how we actually go about measuring intricate disorder or an intricate amount of randomness, right? It's all about processes going towards greater entropy or greater disorder, right? So, for example, when you've got all your particles, for example, moving in a solid versus a liquid versus a gas, right? As you move towards these phase changes of solid to liquid to gas, right, those particles move faster and faster and faster. When they move faster and faster and faster, that is exactly the measurement of more disorder, more randomness, so therefore more entropy. Okay, so they increase entropy. So that's essentially what happens here, right? So generally, when you do these things, right, as things move towards, essentially moving away from solid towards liquid towards gas, right, those particles can move faster and faster and faster, and therefore will increase their entropy. Okay, we've also got this other thing here known as Gibbs free energy, which is delta G. And we're not going to really do too much with really both of these, entropy and delta G here, Gibbs free energy. We're not going to really use these much, or really at all, when it comes to being able to measure them, like literally using measurements. Our goal here is really just to kind of use them as determining factors, right? So in this example here, especially when it comes to delta G, the value of this will determine if a reaction is spontaneous or non-spontaneous. It's kind of similar in how we go about determining if a positive or negative delta H means endo or exothermic. It's very similar to Gibbs free energy. It's delta G, right? If delta G is positive, is it spontaneous or non-spontaneous? If delta G is negative, is it spontaneous or non-spontaneous? Kind of similar to enthalpy, delta H, okay? Now let's talk a little bit more about entropy. Again, entropy is randomness, disorder, chaos, stuff like that, okay? Now, specifically, the following will result in an increase in entropy, right? So kind of playing off what we just saw on the previous slide here, phase changes, right? Anything moving away from being a solid towards a liquid or towards a gas is generally going to be entropy increasing, right? So for example, if you've got a ice cube, solid water, turning into and phase changing from solid water to liquid water, that's a phase change moving away from a solid toward liquid towards gas. So that's going to be an increase in entropy. And that should hopefully kind of make more sense, right? Because essentially, guys, that solid water is way more movable than that liquid water is. Or excuse me, let me flip that on its head. But that liquid water is way more movable, right? Its particles can move a lot more freely than the solid particles can. So, keep that in mind, right? It's all about the movement of the particles, right? Can they move more or less? Well, that's going to result in less or more entropy. More gas particles as products than reactants. Well, how do we go about measuring that? You go about measuring that by looking at the coefficients, okay? So if we're talking about more gas particles as products than reactants on the right-hand side, well, if we're talking about products versus reactants, well, this has got 2 moles of gas, and we've got an invisible 1 here, plus a 3 here, so we've got a total of 4 moles of gas. When we look at this here, we've got less on the right, less on the left, and more on the right. These are our products here. We've got more gas particles as products on the right-hand side here, okay? So therefore, this is an increase in entropy in this example here, okay? Solids being dissolved in water, right? So an example here would be if you took solid sodium chloride, NaCl, and dissolved it in water, right? It's going to turn into its ions, right? This kind of makes sense because it's almost similar to our very first example of phase changes from solid to liquid, right? In a way, this is a phase change to a degree of solid becoming liquid, right? An aqueous solution is a liquid solution. In this case here, that's going to be an order or an increase in your entropy, okay? Also, an increase in temperature is going to be another great example of entropy, right? As we know, temperature is the measurement of the average kinetic energy of the particles, right? So if the average kinetic energy of the particles are increasing, so is temperature, And when that average kinetic energy of the particles increase, right, the movement of those particles is going to also increase too. So now, on the flip side here, some of these things are going to result in a decrease in entropy. So dissolving a gas into a solvent, right? That's going to be a great example of when I recently talked about, the idea of carbonated beverages, right? Taking a dissolvable gas and dissolving it into a solvent to create an aqueous solution of a gas, right? So think about the carbonation, aka the CO2 gas, that gets dissolved into a solution of, let's say, Coca-Cola, right? That's going to be resulting in a decrease in entropy, right? Those gas particles of CO2 are getting trapped inside of a liquid solvent to create a solution, right? So they're not able to move around nearly as much. The opposite of anything that causes an increase in entropy from the previous slide. So if I go back to this slide here, guys, the opposite of all four of these things here are going to result in a decrease in entropy, right? So take all these four examples here: phase changes from solid, liquid to gas, more gas particles on the reactants side versus the product side, solids not being dissolved in water, and then a decrease in temperature, right? All these are opposites, so that are going to result essentially in a decrease in entropy, okay? That's one thing. I'm going to skip this here. Now, for a reaction to be spontaneous, okay, if the reaction is spontaneous or not depends on both the delta H, your enthalpy, and the S, your entropy, right? Reactions that are both exothermic with a negative delta H with an increase in entropy tend to be spontaneous. Now, there's no way to know for sure unless you crunch the numbers for, and this is misspelled here, no way to know for sure unless you crunch the numbers and calculate Gibbs free energy. Again, we're not going to do that. We're not going to do any calculations regarding this delta G, this Gibbs free energy. But there's just a couple of things that I want you to be able to know and recognize when it comes to kind of using these phrases here. So again, generally, systems in nature tend to go towards greater entropy and lower overall energy. Okay, lower energy, more stable, and that's a pretty common theme across so many different things we've talked about this school year, right? Think about our reasoning for talking about the octet rule back in chapters 5 and 10, right? Octet rule being everything wants to exist as having 8 valence electrons, right? 8 valence electrons in an atom or in a molecule is stable, right? That's great. Everything wants to be stable and low energy. Okay. Now here is the Gibbs free energy equation. Again, we don't actually use this to do any calculations. All we will use this for is to determine if a reaction is spontaneous or not. That's it. Okay. But here are the pieces of this reaction. Delta G is known as the energy of your system, right? That Gibbs free energy. Delta H, as we know, is our enthalpy or change in enthalpy. T, as we normally know, and C is going to be temperature. And this delta S or S is going to be our entropy or change in entropy for this particular equation. Okay. Now, here's the thing. Here's the thing I want you to know and understand. Okay, and this is what I want you to kind of focus in on here so much more on the bottom half of the slide. If you see a value for delta G that ends up being negative, your reaction will be spontaneous. If your delta G value is positive, your reaction will be non-spontaneous. So here are really the things you need to focus in on here. Negative delta G, spontaneous. Positive delta G, non-spontaneous. And again, this is the exact same kind of rationale when it comes to understanding your different types of reactions being endo or exothermic, right? And it's all based on the sign of your delta H value. Right? Same exact rationale here. Negative delta G, spontaneous. Positive delta G, non-spontaneous. That's the kind of takeaway here, okay? Again, we will not use this equation in class. We will not do any calculations with this equation, okay? But just there to kind of know and understand what it is and kind of what it looks like, right? Now, changing gears a little bit. This is going to kind of be the point which we start to segue towards the second half of this chapter here. So rather than talking so much about delta H and enthalpy and thermodynamics and all that stuff, we're going to kind of start to move a little bit away from this concept of what's known as thermodynamics and start to talk about reaction rates and chemical equilibrium and stuff like that. So this is going to be that segue point here. So reaction rate, it's the rate at which the amount of reactant is used up or product is formed. So it's essentially going to do, it's essentially going to help us when it comes to understanding how quickly the rate at which a reaction forms your products, okay? Essentially how fast the reaction occurs. It's this whole other branch of chemistry, again, segueing away from thermodynamics and towards something called kinetics, okay? It's a branch of chemistry dealing with reaction rates. In order for a reaction to occur, guys, two particles, atoms, ions, molecules, whatever they may be, must collide or hit in order to react, okay? They don't just react by just existing in the same space. They have to actually collide with each other. That's how a reaction actually occurs. So when they do that, though, there's a couple of things that have to absolutely be present when that happens, when this collision occurs. They must first and foremost collide with the proper energy and the proper orientation or arrangement of their atoms. Okay, so those are some things to keep in mind when these reactions actually do occur. The more times that these particles collide in a given amount of time, the faster the reaction occurs. Okay, so if you've got 10 collisions per minute versus 1,000 collisions per minute, you've got a much different rate of reaction, right? Now, there are several factors that affect the number of collisions in your reaction rate, and we're going to kind of talk about each of them, and I want you to think as we progress through each of them. How does each above affect the number of collisions here? So the nature of your reactants, right? So if you've got more unstable, higher energy reactants, they're going to react more readily, right? They're more unstable, they're going to move around a lot more crazy. Their reaction rate is going to be much higher because of it. If you've got a higher concentration or higher amount of reactants, well, that's going to result in more collisions because there's more of that substance in a small amount of space. Temperature, for example, right? If you've got a higher temperature, that means all your particles have a higher kinetic energy. They're moving around a lot faster, so therefore higher opportunities for collisions to occur. And lastly, surface area, right? Think of this almost like that example I told you guys not too recently about in chapter 13, right? Where you take your spoonful of granulated sugar versus your cube of sugar in a mug of hot tea, for example, right? If you've got a higher surface area, that's more opportunity for all those individual sugar crystals to react and essentially come in contact with tea, right? If you've got, on the flip side, a sugar cube, only the exterior of that sugar cube is going to actually have come in contact with and collide with the hot tea, whereas the inside of the cube is not going to come in contact with any of the tea. So there's going to be a lot less surface area, so less collisions. Okay. Lastly, the presence of a catalyst, and this is going to kind of be where we start to wind down this lecture video here, talking about the presence of a catalyst, number one, and what a catalyst really is and how it affects our rates of reactions. So first and foremost, the definition of a catalyst. It's a substance that increases the rate of a reaction without actually being consumed by the reaction. A catalyst, what it does is it lowers the activation energy by providing an alternate pathway for the reaction to occur. Okay, so what it means is it doesn't actually change anything in terms of your starting energy versus your ending energy, right? This is still the energy of your reactants. This is still the energy of your products here. Okay, but what starts to happen is here, it lowers the activation energy by providing an alternate pathway. Okay, well, what literally happens here is this. Okay, let me show you the activation energy currently for this particular particular potential energy diagram. Okay, currently the activation energy is this space here, right? Here's your EA from here up to here, right? That's the current activation energy, right? From this dotted line here to this dotted line here, right? If we flip this on its head and change or lower our activation energy, what we literally do here is this. We still start at the same energy, but instead we have a lower, higher point on the curve than we would normally do. So this is going to in turn totally lower our activation energy, right? So this is still your EA here. It's much, much, much lower though, okay? And not only has our activation energy been quite literally lowered, but it provided an alternate pathway, right? This pathway is different than this pathway is up here. They're different pathways, okay? Let me mark the newer pathway with the orange there and this original pathway in purple here, right? Two totally different pathways that are marked here, and they're different pathways, and they both have different or essentially lower activation energies, okay? And that's exactly what a catalyst does. It doesn't really do much more than that. It just allows you to have essentially what seems like a quicker reaction or a higher rate of reaction, but in turn really just lowers the activation energy, so the barrier of entry for these reactions happening are much lower, okay? So they happen more readily and available because of that reason, okay? And that's really going to bring us to the end of lecture video number 3. Thank you guys for watching, and I'll see you in class.